Here we have an example on the same type of stuff that I talked about in the previous video about a basketball or any type of other ball striking the ground and jumping from the ground. And having the ground as the second particle makes the second and third equations in our equation set for the oblique central impact useless. That means we're going to use the first and the fourth steps in our solution. What happens here is that our ball has a certain speed right before the impact, and then it jumps back from the ground with another velocity. Now we need to identify the normal and tangential directions here. Remember that normal direction is the direction where these two particles apply action-reaction forces with respect to each other, the interaction forces. Therefore, this is our normal direction. And with respect to that, the tangential direction is in the horizontal in this case. And the other step that we need to think about is the decomposition of this velocity, initial velocity of this ball into normal and tangential direction. This is the normal direction. Again, this is our normal direction and this is our tangential direction. And we already know that the angle is 60 degrees, so with respect to that we will have a normal component of this velocity and a tangential component of this velocity, v0. The tangential component of this velocity will not be affected due to this impact. That's the first step of our solution. So whatever v0, and since this is 60 degrees, we are talking about cosine 60, it's going to remain as the tangential velocity of the new tangential velocity component of the new velocity of the ball. So if we say that's v, as identified in this figure, this is v tangential. Okay, so it's going to remain the same. The normal component of the velocity of the ball, if we say that we define the normal component's positive direction upwards, like that, okay, this is the positive direction, then this will be in the negative direction, so it's going to have a negative sign. It is a negative v0 sine 60 degrees, and then it's going to jump off from the ground in the normal direction with a velocity of v normal, which we don't know. And the type of information that is available to us is the coefficient of restitution. It's less than 1, which means that we don't have a perfect elastic case, which says that the bouncing back velocity from the ground in the normal direction will be less than the initial case. And that's why in the figure we kind of see that the theta angle is less than 60 degrees, because the normal component velocity is, in an absolute value manner, less than the initial case. Any case, we can actually prove that in a mathematical way, and that's our fourth stage, writing out the coefficient of restitution equation. Remember that in that equation we had the v2 velocities, but since the second particle is a large mass particle with no velocity at all, then this equation is changed into this format, and all we need to do is write out this information of the velocity. Now you please be careful here that we have this minus sign for v0 And the main reason of having that minus sign is with respect to our selection of the anti-coordinates. The positive direction of the and is vertical upward. If you have chosen it vertical downward, then it's not going to be a minus, but then you need to be careful about the velocity of the bouncing ball, as it will be vertically upward. But if you have chosen this as a plus, then it will be a minus sign, because the normal direction in that case would be in the downward direction. Okay, if you chosen the normal direction in this way, which we did not, so forget about this. Since we did not choose this in this way, vertical upward is positive, then this way of presenting this equation is correct, and as a result of that we get a positive velocity, meaning that the ball is jumping up. And then you can do the necessary trigonometric equalities to solve for the rest of the problem, which is asking about this theta. And as expected, it came out to be 54.2, less than 60 degrees, because the vertical component of the velocity has decreased in the absolute value manner.